So then I guess it's time to start. So it's my pleasure to introduce Sophie Grivaux from University of Lille, and she's going to talk to us about typical properties of contractions on LP spaces.
Okay, so thank you very much, Pavlos, for the introduction. And well, thanks to Benjamin and you all for inviting me to this seminar and for being here. So I'm going to talk about a joint work with Etienne Matron and Quentin Menet, and about typical properties of contractions on LP spaces. So yes, I'll try to collapse this so that it won't bother you. So I should tell you that, well, I'm always a bit uncomfortable with Zoom talks because I cannot see any of you. So I don't see how you react, whether something is unclear or if it is going too slow, too fast, and so on. So please interrupt me if anything is unclear, or if you would like me to go back one slide, to go one slide back or something, and I will appreciate it, okay? So, well, I'm going to talk about typical properties. So here is the first slide about, well, the general setting. So we will specify it a bit afterwards, but let's be very simple and general for the moment. So here is the definition of a Polish space. So typicality properties are well studied in the context of Polish spaces. So many of you probably know already the definition, but let me recall it. So it's a topological space which is both separable and completely metrizable, which means that you can define its topology via a distance which turns it into a complete metric space. So, as you all know, being a complete space, it's a metric notion. It depends on a distance, while being a Polish space is a topological notion. So, of course, any separable complete metric space is a Polish space, but there are other examples, and classical one is that if you take, for instance, the open interval 0, 1, and though there's a topology induced by that of R, then you get a Polish space as well. So while will we work in the setting of Polish spaces in this talk? Well, for a very simple reason, it's that the Baire category theorem applies in this setting. So namely, if you take a sequence of open-dense subsets of your Polish space, then the intersection will be dense again. And well, as you all know, a set of this form, a countable intersection of open sets, will be called a G delta set. And I will use a lot the word comeager. So a comeager set is, in a Polish space, is a set containing a dense G delta set. So what is the philosophy of all this? In the Baire category sense, the comeager sets in the Polish space are the sets which are big, right? So they are big in a Baire category sense, of course, and well, you can see this in the following way, that if I take a countable intersection of big sets in the sense of comeager sets, then they are again big, right? So this is why we will use a lot this notion of comeagerness. So this motivates the definition which I wrote here. So it's going to be a very important definition in the talk. So it's the definition of a typical property. So we have a Polish space, which I call X, and a certain property P of elements of X. So whatever property you like, your favorite property. And we say that this property P is typical, or that a typical vector in the space has this property P, if when we consider the set of elements in the space which have property P, then it is comeager in the space. So I wrote down here a very easy example, right? So if for your favorite Polish space, you take the space of real numbers with the usual topology of R, then the set of irrational numbers is of course a dense G delta set. And so I can say that a typical real number is irrational, right? So I should be careful about something here. I would like to spend a bit of time on this definition. It's very easy, but it's usually at this point, very early in the talk, that I lose part of my audience. So I often get asked the following question. So for instance, okay, I say that a typical real number was irrational. So is it true that square root of 2 is irrational? Right. So if you look at the definition, you see that asking this is meaningless, right? You won't ever say that a certain number is typical. Being typical, it's something which is related to a property, right? You consider the set of elements satisfying this property, and either it's comeager, that means it's big, or it's not, and then you don't get a typical property, right? So this definition has to be kept in mind to be comfortable with the rest of the talk, right? And then, well, I put down here another example in a different setting. So if you consider, for instance, probability measures on the segment 0, 1, and you endow this with the Wickstra topology, so of course you get a compact space, so it's a Polish space, and you can wonder about, well, what could be interesting typical properties of elements of this Polish space, so typical property of probability measures. And you can, instance, prove that a typical probability measure is continuous. So this means that it puts no mass on any point, right? The measure of any singleton is equal to 0. It's also purely singular with respect to Lebesgue measure. This you can also prove. And well, if you have another interesting property of measures in mind, then you can try to check whether it's typical or not. So there is also a word of caution here. Typicality, it's like open and closed set, right? A property can be typical or its complement, its negative can be typical, but you can also have properties such that which are neither typical nor atypical in the sense that its complement is typical, right? So, sometimes in many situations, you have a kind of 0-1 law, we will see it afterwards, which tells you that, well, either the set of elements with a property will be comeager or its complement will be comeager, but it may quite often happen that it's not the case. Okay, good. So, well, now let us get down a bit to our subject after these general things. So we will work on separable Banach spaces, usually complex, but it's not always necessary. And I will denote by B1 of X the set of contractions on X, the set of operators of norm less than 1. And our aim is to put on this set of contractions on X a natural topology, let's say, let me call it tau, which will turn it into a Polish space, and we will try to study whether, well, some properties of contractions for this topology tau are typical or not, and generally what happens. So, well, there are plenty of natural choices of topologies on this unit ball of B of X. So, well, perhaps the first one which comes to mind is the operator norm topology. So, well, as you guess, it usually won't work well because in very many cases, for instance, when you take X and LP space, or very many natural spaces, then B1 of X with a norm operator topology won't be separable. So you won't get a Polish space, and this topology is too strong for all purposes. And then you have three topologies which are weaker and which in many cases will indeed turn this B1 of X into a Polish space. So I gave the definitions again in case you needed to be reminded. So there is the weak operator topology, so the weakest of all the topologies we will consider. So if you have a net, or well, in our context, it will be a sequence because things will be metrizable. But Ti converges to T for WOT if you have weak convergence of Ti of X to Tx for every vector in your space. And then you have the strong operator topology. So the definition is much the same, except that instead of asking for Ti of X to converge to Tx weakly, then you ask it to converge in norm. So, well, these two topologies are very well known to people who work in operator theory, as they come up naturally in very many problems. The third one, which is called SOT star, is perhaps not so well known, but it's quite an interesting one in our context. So saying that Ti converges to T for SOT star, the strong star operator topology, means that Ti of X converges to Tx in norm, and Ty star of any functional X star, let's say, converges in norm to T star of X star for every X star, right? So you have convergence of Ti to T for SOT and also of the adjoints, right? So SOT star is the strongest of all three topologies. So if you're not very familiar with these topologies, it may be helpful to have just a picture in matrix form to help you visualize a bit what it means to be, for an operator to be close to another for one of these topologies. So the setting is the following. So we will be in an LP space with its canonical basis, which I denote by EJ. And well, I denote by En the span of the first n+1 basis vectors, so finite dimensional space. And well, let's take two operators T0 and T, two contractions. And then what does it mean for T to be, let's say, WT close to T0? So it means, if you take a basis of neighborhood, it means that for a certain n and for a certain epsilon, this quantity, which I wrote as 1, so PEN of T minus T0, PEN is going to be small, right? So if you look at this big matrix, right, what we are considering is what is in the square box in the left-hand top corner, right? So if this red part denoted by 1 is very close for T and T0, then T is going to be close to T0 for WOT. That's what it means. For SOT, you have to consider the first n columns, right? So this is the part which has rho type as 2. Saying that T is SOT close to T0 means that these first n columns are very similar for T and T0. They differ by an epsilon variation. And then for SOT star, so if you recall, T has to be SOT close to T0 and T star has to be SOT close to T0 star. So this means that both the first n lines and the first n columns and the first n lines have to be very similar, very close to each other for T and T0, right? So for SOT star, you have to have control on both part 2 and part 3 of the matrix, right? So if you have never seen these topologies before, it's, well, you have to recall about it, it's basically very easy to understand these topologies in this context. Okay, so as I promised you, I need topologies which turn the set of contractions on X into Polish spaces. And well, things work rather nicely. So if you have a separable space, then contraction endowed with SOT will be a Polish space. If you have a space with separable dual, then you have the same for SOT star, and for reflexive space, for instance, you have it also for WOT, right? So these are perhaps not the best result which can be derived, but just starting from the bottom of the slide, we will work only in LP or C0, so it's quite sufficient for our purposes. So, just so that you get a very quick feeling of why it is true, it's very easy. For instance, if you have a separable space and you want to show that B1 of X SOT is Polish, then here is the 2 lines proof. You take a dense sequence in the unit sphere and you define this distance between two contraction on X. So the sum over 2 minus n of the distance between Txn and Sxn. And you very easily check that it's a distance which defines the strong operator topology on X and which turns it into a complete metric space, right? And then for the other 2 statements, you just do the obvious modifications to the distance and then you get it, right? So, these 3 topologies are good candidates for our study, let's say. And in the context of LP spaces, or by LP spaces, I mean also C0 of n, it's included somehow in this category, then B1 of X is always a Polish space for SOT, and if P is strictly larger than 1, it's also a Polish space for WOT and for SOT star, right? So this is the setting we will work in, and here is the general question we will be interested in. So sorry, it's the general aim I presented at the beginning of my talk. We have endowed the space of contraction on a certain LP space with a Polish topology, and now we are trying to see, can we find some interesting typical properties of contractions on my LP space for one of these topologies. And here is, for instance, the kind of question one may ask you. You take a natural property of a contraction and you're wondering if it is typical or not. So it's more or less interesting, depending, of course, on the kind of property you consider. But for instance, here are two questions which are very natural and very easy to ask. For instance, if you take a typical contraction on LP or C0 for, let's say, WOT, SOT, or SOT star, is it true that it has an eigenvector or that it is injective, whatever? And also, in relation with the invariant subspace problem, you very naturally ask also, is it true that a typical contraction for one of these topology has a non-trivial invariant subspace? So I will say a few words afterwards, just the next slide on the invariant subspace problem, but I recall here the definition of a non-trivial invariant subspace. It's simply a closed subspace of X, distinct from 0 and from the whole space X, which has the property of being T invariant, so T of M is included in M. So here is my definition again, so that we all see what we are trying to do. For instance, saying that a typical contraction on LP for SOT has a non-trivial invariant subspace means that the set of contraction with a non-trivial invariant subspace is comeager in B1 of LP for SOT. So there is one thing I should point out before I go to the next slide. So I presented 3 topologies. So they were WOT, SOT, SOT star. And I will mainly concentrate on SOT and SOT star a bit. It's tempting to think that, okay, if a property is typical for one of these topologies, then probably it will be typical for the weaker topology or a stronger topology, right? So it's important to have in mind that this is not true at all, right? When you're trying to prove that a property is typical, you're trying to find a set of operators satisfying this property, which is G delta and dense for the topology. But if you change the topology, right, the properties of being G delta and being dense will move in opposite direction, right? So for instance, if you have a set which is G delta for SOT, it will be G delta for any stronger topology, right? But if it's dense for SOT, it will be dense for any weaker topology. So actually, if you have a property which is typical for SOT, there is no reason at all that it should be typical for either WOT or for SOT star, right? We will see examples immediately afterwards, but you have here three topologies and you have three different problems, three different questions, right? So even though sometimes you may your main findings. Okay, so well, I'll be quick about this slide because I guess many of you know many things about the invariant subspace problem, but let me quickly recall what it is about. So it's of course perhaps the most famous open problem nowadays in operator theory. And the very general question is whether when you have a bounded operator on a separable infinite dimensional Banach space, you can find a non-trivial invariant subspace for your operator. So this question was solved in the negative by Enflow in the 70s, and he constructed counterexamples on some complicated Banach spaces. And then afterwards, some other counterexamples were constructed by Reed and well, more tractable and with the advantage of that what could carry them out on some classical Banach spaces like little L1, like little C0, or well, another interesting space for Reed's type examples is the direct L2 sum of countably many copies of the James space, right? So it's an interesting space as well because X double dual quotiented by X is separable. And Reed also constructed examples of operators on L1, which had no non-trivial invariant closed subsets. So the definition is the same, but instead of talking about subspaces invariant, you talk about subsets. And well, Maria Roginskaya and myself could in fact produce a unified proof of all these Reed's type construction on a rather large class of non-reflexive Banach spaces, but they remain non-reflexive, of course. And well, another very important step in the study of the invariant subspace problem is the Argyros-Haydn result of 2011, where they proved that there exist Banach spaces such that every operator on X is a compact perturbation of a multiple of the identity. And this implies, of course, that every such operator has a non-trivial invariant subspace, right? And then there were further results by Argyros and Motakis about the reflexive case, that you could construct reflexive Banach spaces on which every operator has a non-trivial invariant subspace. So actually, the invariant subspace problem is widely open for reflexive spaces. So we have no clue, basically, about whether it's possible to find a reflexive space which supports an operator without non-trivial invariant subspace. And of course, most importantly, it's open in the Hilbertian setting. So, well, LP spaces already provide a very interesting class of Banach spaces in this context, because on the LP scale, well, for L1 and C0, you have Reed's counterexamples, and well, you know that there are operators on these spaces without non-trivial invariant subspaces. Then for L2, you have the very interesting Hilbertian case, and well, LP spaces for P not equal to 2 are reflexive spaces, but which may have very tricky properties. So, well, it's already interesting to look at the question of typicality of operators with an invariant subspace for LP spaces, right? So I rewrote here the question about the question which is of interest to us, that well, for one of these topologies on B1 of LP, is it true that a typical contraction for this topology has a non-trivial invariant subspace? Okay, so what do we know about that? So I will begin with the Hilbertian setting because very many things are already understood in the Hilbertian setting, and it's not due to Etienne, Quentin, and myself, but this study was already carried out by Tanja Eisner and also by Tanja Eisner and Tamas Matrai. And they studied typical properties of contraction on L2 for WOT and for SOT. So here is a sample of the results that they proved. So the first one is by Tanja Eisner herself, that, well, a typical contraction on L2 for WOT is unitary. Right. So as a consequence, you get very straightforwardly that a typical contraction on a Hilbert space for WOT has a non-trivial invariant subspace. There is no mystery about that. And well, in the SOT setting, Eisner Matrai proved a rather nice result, which gives you a fairly complete description of typical properties of contraction. So a typical contraction on L2 for SOT is unitarily similar to the backward shift of infinite multiplicity on, well, the countable L2, the direct L2 sum of countably many copies of L2. Right, so just in case you're not completely familiar with this, I rewrote the definition of the backward shift of infinite multiplicity. So it's defined of the space of L2 valued sequences such that the sum of the norm of xn to the square is convergent. So that's my L2 sum of L2. And if you have such a sequence, x0, x1, x2, etc., you just shift it to the left and cancel the first coordinate. So that's a rather strong result, right? Because you get that the orbit of a single operator under unitary similarity, unitary equivalence, is comeager in B1 of L2 SOT, right? So this theorem has rather strong consequences because it tells you that, well, if you want to check whether a certain property of contraction is typical for SOT, then you just look whether B infinity has it or not. And then, well, if it has it, then this property is typical, right? So in particular, a typical contraction on L2 for SOT has eigenvectors. This is because B infinity has plenty of eigenvectors. It's obviously not injective, right? And also any number of modulus strictly less than 1 is an eigenvalue. And in particular, typical contraction for SOT has invariant subspace for very trivial reasons, right? So in this case, you have a very clear-cut description of things, but well, you don't get anything especially out of the ordinary as far as the question of typicality of operators with or without invariant subspaces is concerned. And also, because I will talk about it a bit later on in the talk, I should point out that this theorem implies that a typical contraction on SOT star is such that T star is an isometry, right? So this is a natural statement when you come to proof, but well, I won't have time to say a lot about that, but still I will try just to outline one or two ideas. So what is the general method of proof of results of this kind, just so that we have seen something. So I wrote here the theorem by Tanja that typical T for WOT is unitary. So, well, you can read the proof here. It's the first part is very straightforward. You write what it means for an operator on L2 to be unitary with proper quantifiers involving a dense sequence in the unit sphere of L2, and you observe that since sets of the form, the sets of T such that y scalar Tx is bigger than delta in modulus RWOT open, then you get something which is WOT G delta. And well, the hard part of the proof, it's not very hard, but it's not obvious completely, let's say, is to prove that U of L2 is WOT dense in B1 of L2. So it follows actually from results of Vladimir Peller, and this is what Tanja Eisner used in her proof, but you can also prove it using the Nagy-Folyás dilation theorem. Okay. So, well, so here is a kind of formal proof, but well, if you just want to get a feeling of what's happening, here is a proof with hands, right? So you want to look at typical properties of contractions on L2 for WOT. So for WOT, the map, if you fix a vector x in your Hilbert space and you consider the map which maps an operator T to the norm of Tx, it's not continuous for WOT. So what a typical contraction for WOT will try to do is to maximize the norm of Tx. And in the Hilbertian setting, a typical contraction can do it. So a typical contraction for WOT is going to be such that the norm of Tx is equal to the norm of x for every x. So it's going to be an isometry. And since the map which maps T to the norm of T star x is also not continuous for WOT, also a typical contraction will maximize all these norms. And so you get that a typical contraction is going to be such that T is an isometry and T star is an isometry. So you get something unitary. And if now you go back to the Eisner-Matraille result that a typical contraction for SOT is unitarily similar to B infinity, then with this argument waving hands, you can get a feeling of why this is true. Okay, for SOT, the maps T maps to norm of Tx are going to be continuous. So this part of the argument is destroyed. I cannot get that a typical T is an isometry. This is obviously wrong. But the part for the adjoint remains. And so a typical SOT contraction is going to be such that T star is an isometry. And for isometries on Hilbert spaces, you have the Volt decomposition theorem, which tells you all about isometries, right? And once you have this, basically you have to compute multiplicity and so on, and you get easily that a typical T is unitarily similar to B infinity, right? So this theorem is not as strange as it may seem at first glance when you have this, this idea in mind. Okay, so, well, just a quick word about SOT star in the Hilbertian setting. So typical properties of contractions for SOT star I are by far not so well understood. So in a previous work with Etienne Matron and Quentin Menet, we studied this already in the Hilbertian setting. And for instance, we could prove that a typical T has no eigenvalue. It's not a very complicated argument, but you see that it's very different from what happens for SOT, for instance. And then, well, if we are wondering whether a typical T for SOT star has an invariant subspace or not, then, well, it's still true, but the reasons are much less trivial, right? It's not because it's unitary or because it has an eigenvectors. So the only way to answer the question, I mean, the only way we could think of was to use a highly non-trivial result, which is the famous Brown-Chevreau-Percy theorem, which tells you that if you have a contraction on a Hilbert space whose spectrum contains the whole unit circle, so you have big spectrum in this sense, then T has a non-trivial invariant subspace. And so, well, once you have thought about this theorem, well, you can show without too much trouble that the spectrum of a typical contraction on LP, or C0 for what matters, for SOT star is such that the spectrum is the whole closed unit disk. So it contains the unit circle, and in the Hilbertian setting, it allows you to conclude that the typical T for SOT star has a non-trivial invariant subspace. Sorry, this is the baby phone because my son is still sleeping, but okay. And well, but it's a rather complicated argument, and well, I would be very happy if we could prove in a more direct way that a typical contraction on a Hilbert space for SOT star has a non-trivial invariant subspace. But well, for the time being, we don't know how to do it differently. Okay, so now let's get to work a bit. So what happens for SOT typical contraction on LP for P not equal to 2? So there is an extreme case, which is P equals 1. And then for P equals 1, the situation is surprisingly similar to the Hilbertian one. I mean, L1 is not Hilbertian at all, but things behave in much the same way. So here is the theorem we could prove. A typical contraction on L1 for SOT is such that T star is an isometry. So this part of the Hilbertian result remains, and also such that any number of modulus less than 1 is an eigenvalue of infinite multiplicity, which is a thing we had also in the Hilbertian setting, because a typical T was unitarily similar to the backward shift of infinite multiplicity. So consequently, a typical contraction on L1 for SOT has a non-trivial invariant subspace. And for a reason which is rather trivial also, it's just existence of eigenvalues. So, well, I won't tell you about the proof of this theorem, but it's not very difficult to prove. I mean, one has to work a bit, but it's not a terrible work, and the situation is rather well understood for P equals 1. But it's still a bit surprising that P equals 1 and P equals 2 behave in much the same manner. So, okay, what happens now when you exclude the value 2 and the value 1? And well, the embarrassing thing is that, well, it's hard and we do not know really. So here is a theorem we could prove. So which tells you that when P is strictly larger than 2, then a typical contraction on LP for SOT has no eigenvalue. So if you recall the Hilbertian result from Eisner and Matrai, it was telling you that the typical contraction on L2 was such that any lambda in the unit disk was an eigenvalue of T, and we could deduce the existence of invariant subspace in a trivial way from that. Well, so what this theorem tells you is that well, the situation is very different for P larger than 2, and you have no eigenvalue, and so you cannot conclude that you have invariant subspaces in such an easy way. So here is the theorem. So actually, I will spend basically the rest of the time trying to tell you a bit about this theorem and about its proof, because that's the core of our work. And well, and a key step in the proof of this theorem is given by a rather intriguing statement, which gives you a link between typical properties for SOT star and for SOT. So I told you at the beginning of the talk that if you had a property which was typical for SOT star, it had no reason at all for being typical for SOT, right? And for instance, for P equal 2, there are rather straightforward examples of properties which are typical for SOT star and which are not typical for SOT. But the surprising fact is that when P is strictly larger than 2, then this becomes true. And for many properties, it's much easier to work with SOT star. I will try to explain you afterwards why it is the case. And so you can transfer typicality results from the SOT star topology to the SOT topology. Right, but this statement has some content, right? It's not something trivial, which you can prove by just writing G deltas and comparing topology. So basically, the theorem that a typical contraction on LP for SOT has no eigenvalue will follow from the theorem in the middle of the page comparing these two topologies, and the proposition that for P strictly larger than 1, a typical contraction on LP for SOT star has no eigenvalue, right? And since the proof is rather straightforward, I will try to give you a sketch of it. So it's straightforward, but when it's written on a slide like that, it always looks complicated, but it's not really. So you consider the set of contraction on LP, which admit an eigenvalue, and we are going to prove that it is meager, right? So the non-trivial part of the proof is to show that this set F is F sigma, right? And well, we write this set as a union of sets FQ, and FQ is defined as the set of contractions which have an eigenvalue, but you restrict the parameters lambda and x to belong to the closed unit disk time CQ, where each CQ is a closed ball in LP, right? And the important point about this is that these balls are weakly compact. And then, well, this set FQ is actually a projection of this product set, which has wrote as curly FQ. And this set is closed for the topology SOT star times the norm topology times the weak topology. And the reason it's here actually that the topology SOT star is very important, and that the argument would break down if we were to use the topology SOT instead. So perhaps it's slightly bit technical and a bit difficult to follow, but well, the thing to recall about this proof is what I wrote in kind of yellow at the bottom of the page. If you have a sequence of vectors which converge, if you have a sequence of functionals which converges in norm to a certain functional, and then another sequence of vectors which converges weakly to a vector, then when you apply your functionals to the vector, then, well, there is a weak which shouldn't be here, but the scalar products converge to the limit you expect. Right, so this is what I wrote. Since Tn star of x star converges in norm to T star of x star, and Xn converges weakly to x, then when I take the scalar product Tn star of x star scalar Xn, then it converges to T star of x star applied to x. And this is here that we use the SOT star topology, because when we are trying to prove that our set is closed, then we move the adjoint to the other side. And because of SOT star, we have convergence of Tn star of x star to T star of x star, right? So the topology SOT star is extremely convenient because of this argument. It may look like, well, it's not so very different from SOT, etc. But in very many proofs, you can shift the adjoint to the other part of your duality brackets, and things become much easier. Right, so in this way, you show that each of your set FQ is closed for SOT star, so F is F sigma, and then you have to prove that the complement is dense, but that's pretty straightforward. So here is what we proved with this simple proof, that when you have a typical contraction for SOT star, then it has no eigenvalue. And then there is the bulk of the proof, which is to prove the statement about really LP spaces for P bigger than 2, that if you have a set which is comeager for SOT star, then it's also comeager for SOT. Right. Okay, so let me try to give you an idea of proof. And well, I think the most intuitive way to see it is to see it in terms of Bannermaster game. So what in general is a Bannermaster game? So you have a Polish space, which I called E here because X was already taken for something, and a certain subset A of my Polish space. And well, we want to characterize when the set A is comeagre in E. And we characterize it in terms of games in the following way. So we have two players, 1 and 2, and they play alternatively open sets in E. So U0, U1, with the rule that each set must be played inside the previous one, right? And player 2 wins the run if the intersection of my sets UN is contained in A. So each player has its own strategy, and player 2 wants to have the intersection sitting in A, and player 1 tries to have it, on the contrary, not sitting in A. And the set A...
Sophie, excuse me, the intersection should be non-empty, probably. Containing to A and non-empty,
right? Of course, you're quite right. Thank you. It's Gilles, right?
Yes, it's Gilles.
Yes, okay. I cannot see you on my screen, but okay. Thank you.
You can hear me, this is what matters.
Yeah. Thank you. So they are non-empty, exactly, sorry. And well, what was I saying? Okay, and the set A is, the theorem about these Bannermaster games is that the set A is comeagre in E if and only if player 2 has a winning strategy in this game, right? And well, without loss of generality, you can require the sets UN to be picked from a given basis of the topology of E. So that's a very classical procedure for proving that a set is comeagre. And well, so in our context, what are we going to do? We're going to play games in the Polish space B1 of LP for SOT, right? So this is going to be our Polish space. So how do we play it? So we have a canonical basis. Let me recall that En is the span of the first n+1 basis vectors. And the open sets playing in the games will be, well, SOT neighborhoods of a certain operator A. So they look like this. The set of operators that T of EJ is close to A of EJ, epsilon close for a certain number of coordinates, the first n+1 coordinates. And then player 1's at even moves plays a set like that, so associated to certain parameters, n2k, a2k, epsilon 2k, and player 2 plays odd moves with another set. So they are all non-empty, right? And then they have to be decreasing, right? u2k plus 1 has to be sitting inside u2k. And so in terms of operators, what are we doing? So let's say that at the move 2k, player 1 has played a certain open set. So it's a neighborhood of a certain operator a2k. And then at the next step 2k plus 1, what are the rules of the game? What must player 2 do? So it can vary a bit on the first columns on what has been played by player 1 at the 2k's move. And then he has freedom on the right-hand side to play what he wants. But the tricky thing is that the operator must remain a contraction, right? And that's exactly the point where player 2 may have a strategy to win the game. So anything provided that the operator remains a contraction. And it's here that the condition that P has to be larger than 2 appears. So it appears through a very elementary inequality. So it's to be found in plenty of papers and books and whatever. And well, this inequality has in our context the following interesting consequence. So we have a contraction, let me call it T, on LP. And we suppose that this contraction has a norming vector. So there exists a vector f of norm 1, such that the norm of Tf is equal to 1. That is, my contraction is of norm 1, exactly right. And then what happens, if I take a vector in LP whose support is disjoint from the support of F, then the support of TF is going to be disjoint from the support of TG. Right. So since it's really the crux of the proof, I will spend 3 minutes to just tell you why a thing like that is true. So it's a simple statement. So I have my norming vector f, and then I take any vector in LP whose support is disjoint from that of f, and then I apply my elementary inequality to the quantities Ej star of Tf plus lambda Tg and Ej star of Tf minus lambda Tg. So if you look at the inequality again, right, it's very classical in the context. You have u plus v to the power p and u minus v to the power p. So this is exactly what you get here on the left-hand side. And then you have the right-hand side, which tells you that, well, this sum is bigger than something. Then we sum over all coordinates. So what appears on the left-hand side is norm of Tf plus lambda Tg to the power p, and then the same thing with a minus sign. And then on the right, we get 2 times the norm of Tf to the power p plus, well, somewhat ugly sum, but who cares, right? And then we use our assumptions that f and g have disjoint support. So the quantity on the left-hand side, we can compute it, and it's 2 lambda p norm of Tg to the power p, plus 2 times the norm of Tf to the square. And this norm of Tf, which is equal to 1, cancels. And what remains is what I wrote on the last line. And now, since p is bigger than 2, when you make lambda go to 0, what you get is that your sum of a j of Ej star Tf to the power p minus 2, etc., is going to be 0, right? And so if you have a j which is in the support of Tf, then it means that Ej star of Tj has to be 0. And so the intersection of these two supports is empty, right? So if you have a non-zero coordinate for Tf, then the same coordinate has to be 0 for Tj. Right. So why is it relevant in our context? So, well, it's relevant through this somewhat ugly proposition, but that's really what's important. So if you have an operator so defined on my finite dimensional space spanned by the first n+1 basis vector, which has the property that this operator is of norm 1, it has as few norming vectors as possible. That is, all the norming vectors are unimodular multiples of a single vectors, and moreover, for these norming vectors, you have all coordinates are non-zero, and all coordinates for the image are also non-zero. Then, well, you can apply the argument I gave you previously, and basically it tells you that if I have an operator such that the matrix, the block 1 in the left-hand corner is very close to this matrix A, then if you want the operator T to remain a contraction, then basically what you can add on the remaining of the first n lines has to be very small. right? So this is interesting in terms of games, because if, let's say, player 2 has played in his left-hand corner an operator satisfying assumption star, that is an operator which has a norming vector and with these properties and so on, then on the next move, player 2 basically can play only something very, very small on the first n lines. So he cannot perturb it. He can play below the first n lines, that's not a problem, but on these first n lines, what he plays is essentially 0. And this forces a structure on the operator which allows player 2 to have a winning strategy for the game. And he can ensure in this way to remain in the proper set and so on and so on. So this part is a bit technical, but well, I just wanted to try to carry out, to pass through the idea that, well, because of this rather straightforward statement for contraction on LP spaces for p bigger than 2, then you can devise a strategy for these Bannermaster games, and so prove the statement we were looking for. Okay, so it's not a surprise that the proof completely breaks down for p between 1 and 2. And actually, I mean, we worked a lot on what happened for p between 1 and 2, and there are quite different phenomena, but we are not able to answer the analogous question. Well, is it true that a typical contraction on LP for SOT has no eigenvalue? We don't know at all. You see, if you imagine the scale of all p's, then a typical T has eigenvalue for p equals to 1 and 2. It has no eigenvalue for p larger than 2, and between 1 and 2, then we don't know. Perhaps a typical T has eigenvalue in this context, but we are unable to prove it currently. And more frustrating still, we don't know if it is true for any p except 1 and 2 that a typical contraction on LP for SOT has a non-trivial invariant subspace. Well, it's quite tempting to try to look at, well, criteria ensuring the existence of invariant subspace and so on, and you try to apply them, but basically nothing works. And we are left with this question, so I leave it with you as well. So what one can prove, it's not very difficult, is that a typical contraction LP for SOT has always a non-trivial invariant cone, right? It follows from results of Vladimir Müller, but it's a rather straightforward application of some spectral properties of typical contraction plus the results of Vladimir. So, well, to finish, I give you here, well, a summary of what we know about typical properties of contractions on LP for SOT. So about spectral properties, well, we know that the spectrum of a typical contraction is always a closed unit disk, and it's not difficult, really. About the property of the adjoint being an isometry, we have seen that it's true for p equals 1 and 2. And one can prove that it's not surprising that it's not the case for other values of p or for C0. We know that T has a non-trivial invariant closed cone, except for the case of C0. Vladimir's result apply in the case of Banach operators on Banach spaces which do not contain C0. And well, we don't know what happens for C0. Then if we wonder whether a typical contraction have eigenvalues, what is the point spectrum, then we know the answer for p equals 1 and 2. We know for p larger than 2 that the point spectrum is empty, and we can also prove it with a different proof, but we can also prove it for C0. But for p between 1 and 2, we don't know. And for the most important question, whether T has a non-trivial invariant subspace. We know it for 1 and 2, but we don't know for other values of P or for C0. So, well, there are still plenty of things to be done in this context. Okay, so I believe I will stop here. So thank you very much for your attention.
Thank you, Sophie. That was very interesting. So we can open for questions now.
Well, one question maybe, if I can you hear me, Pavlos?
Yes, yes, I can hear
Okay.
you.
So, Sophie, nice lecture as usual. Two questions, actually. One about something you certainly know very well, the so-called 0-1 topological laws. That is, concretely, it would mean that if you have a bare measurable collection of operators and everything will be bare measurable in your context, if you have, say, an asymptotic property, then it will be meager or co-meager in a certain sense. You certainly know what I mean.
Yes.
Is it of any use in your context?
Yes, we do use it. We use the topological 0-1 law. And in our context, it says that when you have a set which has a bare property, as you said, and is invariant by the action of isometries, then it's either typical or its complement, it's typical. Okay. So you can use it for lot of properties which are isometry invariant. Of course, it doesn't give you the answer whether it's typical or non-typical, but yes, we do use it in proofs, of course, quite.
A second question, if I may, is about the Bannermaster game. Mm-hmm. Well, as you know, it's possible to change it slightly by making it harder for player 2 to win if player 1 has a right to impose one open set and one point that the open set of player 2 has to contain. You know, this is the so-called strongly alpha favorable in Choquet terminology. Mm-hmm. And so then if the player 2 wins that game, which is harder to win for him, then it says not only that it's bare, but it's actually G delta. I mean, it's topologically Polish. Could that be used in any way in your context?
I don't know. I mean, there are some results which we proved, but which are more technical. So I didn't talk about this, where it was of some importance to have exactly G delta sets, not just co-meager sets, when we were working in other Polish spaces of operators. So I don't know. Perhaps it may be an idea.
A strong Bannermaster game could help if you really want G delta, as you say.
Yes, yes. I mean,
it's an if and only if, actually. So.
Okay. Thanks for the suggestion. I mean, for the results I presented, well, I don't believe it will change much, but in other kind of Polish spaces, it may be of help, perhaps.
Thank you very much.
Thank you, Gilles.
May I ask a question? So you study a lot whether a typical operator or typical contraction is eigenvectors. Are there interesting questions, or is it more or less trivial if you switch the question to having cyclic vectors?
To having?
Cyclic vectors.
Cyclic vectors. And having cyclic vectors, yes, it's a typical properties. I mean, and it's not very difficult to prove that. Well, you can play with properties of orbits and things like that. For instance, well, if you, well, we saw that a typical contraction on L2 had its adjoint, which was an isometry. If you move to P strictly larger than 2, then a typical contraction had the property that 2 times T star has vectors with dense orbits. So it's very far from being an isometry. So you can play around with properties of these kinds. And yes, but it's well, with cyclic vectors, it's true, but it's not so difficult to prove. You write the G delta and prove denseness, but yes.
So is it also with dense sets of cyclic vectors? Can you do something like that too?
Yes, yes, yes.
Thank you. Any other questions?
If I may speak again, Pavlos, it's rather a comment than a question. And this comment is not due to me, but I was impressed by it a few years ago. This is a colleague from number theory. His name is Pierre Colmez, to name him. And I asked him once, what's his opinion about knowing whether the number e plus pi is an irrational number, which is a well-known open question. Nobody has any clue, I believe, about it. And he told me that if something is untypical, that is typically if e plus pi were a rational number, if something is untypical, there are very, very good reasons for being untypical. So in a sense, it's when it so happens, it's easier to decide. But when something is typical, it is typical for no good reason, simply because it belongs to the fat part of the frame. And I found that very interesting somehow. So and maybe it's something to keep in mind. So again, this is due to Pierre Colmez's comment, but I wish to mention it here. Sorry again for being so talkative.
I think I missed maybe the beginning of the talk. Why is a typical operator is expected to have an invariant subset or not have it? Like what's
Well, I mean, I didn't say during the talk, but I said it answering Gilles' questions, that you have called 0-1 topological law, which tells you in this context that if you have a set of contractions which is invariant by the action of the isometry group, right? And it has the bare property, but it's always the case. Then this set, so you consider in the context of your question, the set of operators with a non-trivial invariant subspace, let's say. So it's obviously invariant by isometry. If you conjugate your operator with an isometry, then if you have an invariant subspace, then, well, you move this property. And so having an invariant subspace, it's a property by this 0-1 topological law, which is either typical or its complement is typical. So either a typical operator has a non-trivial invariant subspace or a typical operator doesn't have a non-trivial invariant subspace. So of course, you know, in the setting of a contraction of LP spaces, it will certainly be easier to prove that a typical contraction has an invariant subspace that it doesn't have. But actually, well, it's perhaps something which I should have said at the beginning. When Etienne and Quentin started this work, we had in mind, you know, to work on other Polish spaces of operators. Now, here we are in the space of contraction, so it's perhaps the most natural. But if you're interested in trying to construct operators of Fritz type, counterexamples to the invariant subspace problems and such, you have operators which have a certain structure, a certain form. I mean, all these counterexamples look more or less the same. And you can try to consider a Polish space of operators of this kind and then look at typical properties inside of this set. So it's much more complicated than what I did here. And as a matter of fact, we did not succeed. But this was the initial motivation for that. And then, so when you restrict to classes of operators which are very ugly and so on, then it may not be completely silly to ask whether, well, a typical operator may not have an invariant subspace, right? especially in spaces where you already know there is a counterexamples.
Okay, thank you.
So then maybe perhaps, Bunyamin, you want to stop the recording?